All right, so the people in Zoom land, you might get a thing about that you agree to have this recorded. So just click yes. And it looks like most of you have your cameras off, and that's totally fine, especially since we're being recorded. Got it. Okay. Okay, so this is physics 1111. I should have said that at first in case you were in the wrong room. So today we're going to take it easy. I'll go over some boring syllabus stuff, and then I'll try to give you a little spiel about why physics is awesome. And if you have any questions before we begin about anything. Okay. So this syllabus is posted on D2L. And so here we are. This is our Monday, Wednesday, Friday class. I guess maybe I should be over here so that people can see me in Zoomland. So my name is Sunny Mantri, and I'm the instructor for this course. This is my email. My office is Rogers 113, which is just down the hall right before the stairs. And my office hours are 2 to 4 p.m. on Monday, Wednesday, Friday. If you want to meet with me in office hours virtually through Zoom or something like that, we can do that as well. Just send me an email about it so that I'm not sitting in an empty Zoom room for 2 hours. So just send me an email that you want to meet virtually, and then I'll log in. And we can use the same Zoom link that's in D2L. Okay. This right here is the statement on COVID by University System of Georgia. And so there's a bunch of online tools in this class that we will use. First is D2L. This is where the syllabus is posted. The Zoom link is posted. There's also a link in here to the recorded YouTube lectures. So I'll post these within 24 to 48 hours after each class so that you can go back and look at things. We will also use Top Hat, and we'll try out some of that today. It's a way for you to interact with the class by, we'll do clicker questions, discussion questions, and you can answer through Top Hat. Because usually when I ask a question, I get silence, and this is a way for you to, without worrying about peer pressure, you can actually answer questions. But feel free to blurt out things as well, unless I'm in, well, blurt them out in the discussion part. First, let's answer the questions and then that. So we'll try a Top Hat in a bit. And then the other online tool is WebAssign. This is where your homework assignments will be posted. You need this registration code. And by the way, for both Top Hat and WebAssign, I believe you can sign up with some free trial grace period, and then you can decide whether you want to purchase it or not. So this is a registration code that you need. Also, usually I post grades on WebAssign. All of them are there, but I think this year they're requiring us to put things on D2L, and that's it's a real pain for me to do that. So I might, what I'll do is I'll have all the grades on WebAssign, so it's always there for you. But every now and then, I'll look at what your homework average is at some point, and I'll just have a column that says homework, and I'll just put in the average rather than entering every assignment and so on. And then your test 1, test 2, test 3, I can easily put. Any questions on that? Has anyone used Top Hat here before? Oh, okay. All right. And any questions so far or anything? Okay, so Zoom again is, I will basically record every lecture and broadcast it. So if you someday just feel like you want to stay in your dorm, you can still attend a class And if you miss class for any reason, you can go look at the recorded lectures. I don't take attendance, but your Top Hat interactive class activities are part of your grade. And so if you miss a class and you miss those interactive questions, then you lose those points. Any questions on that? Okay, so textbook. I don't require that you buy a textbook for this class. I think my notes are pretty awesome. No, I'm kidding. But my notes, the first time I taught the class, were based on this textbook here. So if you are a person that wants to have a textbook, you can get that, but I don't require it. And I think on WebAssign, you get like an electronic copy of it anyway. But mostly, my lecture notes should be sufficient. Any questions on that? Okay. So here is the boring catalog description. The learning goals and objectives of this class. So I think everybody in here in this class is not a physics major, right? So there's I think biology majors, business majors, nursing. Any majors that you want to say that I haven't mentioned? Education? Biology. Biology, education, and you are? Biology, okay. And so this is you're here because you're required to be here. And so a question that you might ask is, why do I care about learning physics if I'm not going to, be solving physics problems as part of my career? And there's a few reasons. One is just, intellectual curiosity. It's like, why do we read Shakespeare? Because you can talk about it at parties. So you can just get a lot of knowledge about how the world around you works. And that just makes you more of an informed person. The other thing is that this course will sort of like an exercise for your brain. It will train your brain to think about problems in a very systematic way, how to look at data, how to make sense of it, how to build a problem-solving strategy, how to execute it. And all of that will help you in whatever field you end up in some way, just that way of thinking, the scientific way of thinking. And then finally, we just live in a very technological world. As you can see here, there's 4 devices here that we're using to teach this class. And so it's just good to know about stuff around you, because otherwise it's a really scary place. If you don't know how any of these devices, you have no sense of how any of them work, it can be a scary place to live. And that's true of all fields. So you should learn about biology and chemistry and other areas as well, just so that you have some sense. You don't have to be an expert in everything, but it's not like completely mysterious to you. Any questions on that? Okay. So this is the course outline. We typically get to around chapters 8, 7, or 8. If we have time, we might go into some thermodynamics towards the end. Typically, I don't cover this chapter 13. We usually run out of time. Let's see. Let's look at attendance again. Like I said, I track it mostly through Top Hat. And then your grading is, this is the breakdown here. You will have 3 semester exams, which will total count for 50% of your grade. If you are one of the Zoom people and you intend to just attend all lectures through Zoom, that's fine. But when we take the tests, those will have to be proctored. And so that means you either take the test in class, or you arrange it through a testing center or something like that. But it can't be a take-home test. And I should also, by the way, say that as I'm saying all of this, I should have actually put this in the syllabus. All of this is subject to change because we live in weird times. Who knows what's going to happen 2 months from now. So assuming everything is the way it is now, this is the plan. Your in-class activities, these are the top hat things, are 15% of your grade. Problem sets are 15% of your grade. And then your final exam will be 20% of your grade. Any questions on that? Yeah. It's mostly based on participation, but every now and then I might give you like 90% participation, 10% correctness, something like that. But most of the time, yes, it's to get you to engage with it. Yeah, I should say a note about the top hat questions that we will be doing in class, quite a few of them. They're not really intended to quiz you. That's not the point of it. Because I'm just telling you some information. There's no reason why I would expect you to immediately get the right answers. But the point of the top hat is more that it gets the gears in your brain turning so that you are actively thinking. This is a very common phenomenon. Like you sit in a lecture often and everything makes perfect sense. It's beautifully explained. And then when you go to do the problem sets, you immediately you draw a blank and you don't even know where to start. And that's a very common thing. And that's because it's the first time you are actually thinking on your own rather than listening passively. And so I'm trying to get you to do some of that in class itself so that when you do attempt your problem sets, then you have sort of a head start. And even the problem sets are not meant to quiz you. There's no reason why everyone in this class shouldn't get 100% on all the problem sets. Because if you don't know how to do something, you can ask me. And so, yeah, it's just a matter of the problem sets I view as your learning outside of the class. So I can't teach you everything just because of time reasons. And so there are some things that you kind of learn on your own outside. Any questions on that? Okay. For your tests, I believe you will be allowed to have a 3x5-inch index card with handwritten notes. You cannot have completely worked out example problems on there, but anything else is allowed. Any questions on that? And they have to be handwritten because at some point in history, someone must have taken the textbook and shrunk it down to a 3x5 card. Although if they managed to do that, they probably deserve some extra credit. But anyway, any questions on that? Yeah.
You want to have one card?
Just one card. Yeah. I would say that you should try to come into the test not needing any cards. And it's just in case you freak out, it's there. And I'll say this, if you come into the test where you're like, you don't know anything off the top of your head, everything's on your card, you will struggle to get the test done in the 50 minutes or whatever. Because every time you read a problem, you have to then go search in the card what's happening. Whereas if you just know things, you can immediately start working on the problem. So you're better prepared if you don't need the card when you come in. Yeah.
Is it front or back or just one side?
Front and back. Yeah. Yeah, again, and I will also emphasize this as I teach. You should, even if you do use a note card, if I were to write a note card as a student, it would probably, I would just probably have 3 or 4 lines of stuff on it. Because if you understand the logical structure of everything, everything else follows from it easily. Whereas if you don't see the connection, the story between the different parts of the theory, then every little fact seems like its own new fact, and then your brain just gets overloaded. Whereas if you just see, oh, this just follows from this, and this just follows from this, then it's just a lot simpler to keep track of things. Okay, I think that's about it for the syllabus, and it may all go to hell in 2 weeks, depending on what happens. But we'll that's the current plan. So let me actually switch, talk about how Top Hat is going to work. So let's go here and go to Top Hat. So I'm going to hit present slides, and then I guess I'll do take attendance. And by the way, so as I teach, everything that I'm teaching will be on the screen. So the lecture slides are on Top Hat, but I'm not, the platform is such that I can't use this Apple Pencil to write on it. So I will actually be looking at slides on a different device, but they're the same slides that are on Top Hat. So every time there's a question that I want to ask you, I will switch from my one device and go to Top Hat. That's where we will answer the question. So you can just keep your eyes on these screens here for the people in class and on your laptop screen for those coming in through Zoom. Okay. All right, let me, so, right, so there's any questions about signing into Top Hat? Is this self-explanatory? Okay, 7901 is the code that you need to enter. So let me go ahead and minimize and keep open here. And then I'm going to start presentation. Welcome to Physics 1, everyone. I forget what kind of animal this is, but anyway, it's welcoming you to Physics 1. It's a what?
A chinchilla.
Chinchilla, that's right. Anybody have a chinchilla? Okay, so as I said, the slides are all on Top Hat. I wonder if this is better. Is that better? I guess that's better. And I will go back and forth between the, so this is on Top Hat. Here I kind of go through the slides. There's the syllabus again, etc. But as you can see, I can't write on this. So I am going to instead now switch here and go to my Notability platform here. And then I will say, okay, we're going to now try a Top Hat question. So 2 plus 2. And then you have to pick one of these. So what I will do is, the way this is going to work is I will display the Top Hat question first on here. We can think about it, take our time understanding what's going on. And then to answer it, I'm going to switch to the Top Hat platform. So there's that question again in Top Hat. And now I'm going to go to the next slide. And then it's going to prompt you. So I'm going to hit start question. And it is going to prompt you to answer. So I've put 1 minute on the clock, as you can see there. It's a little test question. Okay, 5 seconds. All right, let's see what we got. All right. One person needs to brush up on their arithmetic. So 4 is the correct answer. 2, 3, 4. Show your work. Any questions on that? Okay. Then let's try, I think there's another question. Here's a fun one. What kind of pet do you have? I'll add a timer of 60 seconds.
Making sure these will be happening during lectures.
What's happening during the lecture?
We'll be answering these questions during the lecture.
Yeah,
Okay.
that's right. Like right now, right? Yeah, the questions will be of a slightly different nature when we start for real. All right, 5 seconds. Lots of dogs. Some cat people in the audience, a bird, 3 people with reptiles. What are the 2 others? Anyone want to volunteer what the other is?
White tree frogs.
Say it again.
White tree frogs.
Tree
Tree frogs.
tree fox.
Frogs.
3 frogs. Okay. Oh, that's super cute. Okay. Here's another one. My pop culture is really bad. I stole this question somewhere from the internet. See if you guys can figure that one out. Yeah, so what's going on in that question? Some of these are Netflix shows. Some of them are made up titles. And I think there's more than one answer possible, but I may have screwed up and it only lets you enter one answer. If that's the case, then pick your favorite one. Is it allowing you to give multiple answers? No. Okay. I messed that up. All right, maybe I'll give it another 10 seconds. All right, let's see what we got. Well, I don't know what the right answer here is. Oh, I did mark it when I Googled it last time. So Tiger King's Gambit is not a show. Okay. Let's see what else we got. Here's another question. Let's see. I gotta know what I'm starting with. So, all right. Start question. All right, maybe I'll give it another 10 seconds. I'll just let the clock run out. In case someone is trying to figure it out live right now with some calculations. Okay, let's see what we got. We got 4 flat earthers. The correct answer is 48. So the 4 of you could start a flat earth society here at UNG. No, don't do that. Well, here's an interesting question. Does anyone know why is the earth round? Say it again? Exactly, it's because of gravity pulling everything in. So for example, asteroids come in all sorts of shapes, right? They look like potatoes. They're not round. And that's because asteroids are, relatively speaking, pretty small. They're not very big, so they don't have as much of as strong of a gravitational field. Whereas the Earth is, anyone know the mass of the Earth? That is correct. It is about 6 trillion kilograms. So that's a lot of mass, a very strong gravitational field, which is why we're stuck to the ground. And so you can imagine that what if the Earth wasn't round? Maybe here's this round Earth, and then it has some weird structure, coming out, like the Himalayas and the Mount Everest. These are tall mountains, but they're not very tall compared to, say, the radius of the Earth, right? So it's still pretty round, and then there's tiny little variations on the surface of the Earth, which are minuscule in comparison to the radius of the Earth. But if you imagine that there's some really tall mountain that grows really, really high and shoots out into space, what's going to happen is in the end, it's going to collapse due to under its own weight. The gravitational pull from the Earth will be so great that it's not going to be able to grow that much. It's going to collapse and become a smaller mountain. And so gravity has this effect of compactifying everything, and that's why we end up in a planet that's basically evolved. Any questions on that? Yeah.
Doesn't it also have something to do with the fact that it's spinning that makes it more round?
The spinning makes it like more egg-shaped, like the equator bulges out a little bit more. So the spinning has the effect that it wants to fling things out into space, and then gravity is what's trying to pull it back in. And so that's why on the equator, this has to do with centrifugal forces and things like that. We'll touch upon that actually a little bit later. But yeah, the spinning can try to fling things off space. So if you were to turn off gravity, then things would slingshot off into space because of the spinning of the Earth. All right. Now here's a sort of a real physics question that may or may not be non-trivial. So let's see what you guys think about this. So here the question is, I've thrown a ball straight up. It reaches some maximum height, and before it falls back down, and at that maximum height, does it have zero acceleration or non-zero acceleration? So that is the question. All right, so it looks like everybody got it. Let's look at. Okay, so 45 of you say 0, 9 of you say non-zero. So I guess this is a non-trivial question. The correct answer is actually non-zero. Are you giving her I told you
I looked
so?
at her and I said, I picked non-zero because it's physics and it seems like the wrong answer, so I picked it.
That's good
Why
reasoning,
is
yeah.
it non-zero?
Why is it non-zero? Well, let me ask the question in a slightly different way. What is zero? There is something that is zero when it's up there. It's the velocity that's zero.
Oh.
Oh, that's right. So the speed comes to, as it goes up, it slows down, comes to a stop. That's when its velocity or its speed is zero, and then it starts to fall back down and start to pick up speed again. What is acceleration, on the other hand? Any car people?
The rate that you're taking up speed, the rate that you're-
It's not funny.
That's right. You're jumping ahead, but yes, that's correct. Good. Good. So if there's any car people in the audience, which I'm sure there is just by statistics, you guys know that when you talk about how badass a car is, one of the things they talk about is its acceleration. So they'll say things like it goes from 0 to 60 in some ridiculous amount of time, right? So something can go from 0 to 60 in 5 seconds, then it's a really powerful car. It can have a lot of acceleration. What they're talking about is how quickly can it change its velocity. It was at 0, then a little bit later it's at 60 miles an hour. How quickly can it get from 0 to 60 miles an hour? That's acceleration. So acceleration is the rate of change of velocity. How quickly can you change the velocity? So when you throw the ball up, what is happening is its velocity or its speed is decreasing. It comes to a rest, and then its speed starts to increase again in the opposite direction. So right when it's at the very top, it is still in the process of changing its velocity. If it had 0 acceleration, then it would just sit there and not move. Like if you have 0 acceleration in a car, you're just going to be sitting there in the parking lot. You're not going to go anywhere because you have no acceleration. You're not able to change your velocity. So because the object is in the process of changing its velocity, it has non-zero acceleration. Another way of thinking about this is that accelerations are caused by forces. So if you push on something, you change its velocity, it starts moving. And as someone here mentioned, the Earth's gravitational force on the object is always there, right? It's always pulling down on the object. So there's always going to be an acceleration, and that happens to be 9.8. By the way, prepare to have your minds blown about where that number 9.8 comes from. It's a beautiful piece of physics. We will actually derive why the acceleration due to gravity is 9.8, and it's a thing of beauty. Any questions on that? Yeah.
So acceleration is like.
It's not like potential. That's a separate concept. But I should say, we will go through very carefully the definitions of all of these things, and we will introduce the concept of potential energy a little bit later on. And what did you have in mind when you're saying potential?
Like how much it can accelerate or change its velocity.
Right, because the word potential has a specific meaning in physics. So I was wondering if you were referring to that or you're just using it like in the English language. That's right. It's I wouldn't say so much it's potential. It's because it's not that it's about to change its speed. It is changing its speed. It's already there, changing its speed, and that's why it has acceleration. Yeah. But yeah, I think maybe what you mean is in the sense of a car that can go from 0 to 60 in 5 seconds, it has the potential to have large acceleration. Whereas another car that takes 5 minutes to get there doesn't have the potential for large acceleration. All right. Okay, let me switch now to here. So in the last 10 minutes, I'm just going to kind of give you a broad overview of physics as a topic. Why do we study it? What is its point? So physics is, it aims to provide an understanding of all of the natural world and its inner workings around us. And by the way, you don't have to furiously take notes. This is more of a just a fun intro to the subject. We will start for reals in the next class. So basically all kinds of questions you can ask about our universe. It basically tries to uncover the fundamental laws that govern all the phenomena that we see in our universe. So we can start with some concrete questions like how do the stars and the planets move? Or how does one determine the path of a projectile like a baseball or a rocket? Why is the sky blue? Why are sunsets orange? These are questions that will be answered actually more in physics too. What is the structure of matter and energy, right? When you look at this table at a microscopic level, it's made up of atoms. So again, fundamentally, what is this table? That's a question that we're asking. What are the fundamental forces in nature? We classify them into 4 types. There's gravity, there's the electromagnetic force, there's the strong nuclear force, and then there's a weak nuclear force responsible for radioactivity. And it turns out that all the phenomena that we observe in the universe are a consequence of one of these 4 forces. So that's another power of physics. It has a very unifying capability that you don't have a million different explanations for a million different phenomena, but rather you have one simple theory that can explain many, many things. And that actually brings me back to the whole spiel I gave about note cards. You should think about this unifying principle also in your note cards. You don't want to write down every single fact. If you can understand how all the facts emerge from some underlying principles, then your note card will actually be very simple. Maybe I should give extra points for how sparse your note card is. No, I won't do that. Let's see, how did galaxies, stars, and planets form? Or for that matter, how did the universe come into existence? All these kinds of deep questions can be approached in physics. Now, along the way, we get some practical utility out of it. So for example, there were some nerd scientists back in the 1800s. They were like, what is matter made of? It's an atom, it's got an electron. They weren't even thinking about building television sets or satellites or anything like that. They were just trying to understand the structure of an atom. And they couldn't even envision that someday, actually, this turns out to be really useful. They discovered the electron, and we can build circuits, and we can turn light bulbs on. All of this comes to us as a side benefit. So there's sort of a branch of physics that's the pure research, which is where you're just asking questions, trying to understand how the world works. And then there's applied physics, where you're trying to take the principles you've discovered and do something with it. And the really, really applied physics is basically engineering, right? So that's when you build planes and dams and satellites and medical imaging and so on. So as I talked about this unifying idea, a very interesting thing that you may or may not know is that you may have heard all these different names of physics theories, right? You may have heard about classical mechanics, then you may have heard about special relativity, you may have heard about general relativity that's associated with Einstein, then you may have heard about quantum mechanics, less well known as something called quantum field theory, and so on. So one of the questions you might ask is, well, how do I make sense of all these different things? If I'm trying to describe the world, there's got to be one physics theory. So why do we talk about quantum mechanics sometimes, and then we talk about Newtonian physics other times? What is going on here? And it's sort of a beautiful thing. What's happening is that each one of these theories classical mechanics, special relativity, general relativity, quantum mechanics, quantum field theory, etc., they are very good at describing a wide range of phenomena in the universe, but not so good at describing other phenomena that are not within that range. Now, the quest of theoretical physics is to find one unified theory that describes everything all at once. And we have not yet achieved that. So classical mechanics, which is what is going to be the focus of this course, was developed by Newton, Galileo, and so on. And what they did is they were just observing things that they could observe in the 1600s. So they were looking at stars and planets moving. They were looking at, I don't know how true it is, but Galileo dropped something from the Leaning Tower of Pisa. And then he was trying to explain, why objects fell the way they did. So those are the things that they were capable of observing. And so they were very successful at describing those things with classical mechanics, which is the subject of this course. But then a little bit later on, people got a bit more sophisticated. And they discovered subatomic particles, and they were able to accelerate these subatomic particles to very, very high speeds close to the speed of light. And then they saw that Newton's equations were not working anymore. They were breaking down. And so Einstein came along and said, well, actually, you need special relativity to describe phenomenon where you have particles moving very close to the speed of light. Something weird happens when that happens, and so you need a different theory. And so on and so forth. General relativity is something that combines Newton's gravity theory with special relativity. You get to put those together, you get general relativity. Quantum mechanics describes the physics of a subatomic phenomenon, and quantum field theory puts together quantum mechanics and special relativity. So here, just for ambiance, I've kind of put some central unifying equations from all these different little sections. So this is classical mechanics, Newton's second law, special relativity, quantum mechanics, general relativity, and so on. Okay. Now, in the last couple of minutes, let me say that one of the things that you should keep in mind is, well, how do we know that we're ever right? Because for 300, 400 years, Newton's classical mechanics seemed supreme. And then Einstein came along and said, well, actually, it doesn't quite work. You need something better called special relativity. And then someone else came along and said, well, actually, when you look inside atoms, none of them work. You need quantum mechanics, and so on. And so in some sense, it seems like a hopeless thing. How is it that planes continue to fly, right? Planes were built to fly based on Newtonian physics. Einstein's coming along and saying, that's all wrong. Why are we all of a sudden crashing, right? So the thing to keep in mind here is that physics is sort of a progressive thing, where when Einstein came along and proposed special relativity, he had to make sure that because Newton's theory was tested so well, it's so good at describing planetary motion, so good at describing all the other things, that when you took special relativity and you took the limit where the object is not moving so fast, close to the speed of light, then you should recover all the predictions of quantum mechanics. It's often called the correspondence principle. And so, in fact, that is true of all these things. If you take the limit, they reduce to the previous theory that was making all these predictions. And this is one of the surest way to spot a crackpot. I'm a physics professor here, so I often get emails from people saying they have a whole new unified theory of everything. And Einstein and Newton, they were all wrong, completely wrong, and this has upended everything. And here's my new theory. I immediately know to delete that email, because any good scientist would know that if you're proposing a new theory, you should take the right limits and reproduce all the predictions of the older theories. Otherwise, planes will fall from the sky just because you have a new theory. All right, I think I'm out of time, so let me stop here. I'll see you guys on Wednesday.